Welcome to today's webinar, an overview of copper pillar technology. We're joined today by Dr. Craig Hillman, the CEO of DFR Solutions. He has nearly 20 years of experience advancing electronics reliability through a deeper understanding of the underlying physics. He and the DFR team continue to serve the electronics industry by exploring current and emerging technologies, sharing their knowledge through services, software, and education. Today, he'll be discussing copper pillar technology, covering the benefits and limitations, dimensions and geometries, and what we know about the reliability and best practices.
Thanks, Ed, and thanks everyone for joining us today on a discussion on the overview of copper pillar technology. It's a very exciting kind of newish kind of first level interconnect between die and substrate. But there's, as with most new technologies, there is a lot of hype and some degree of uncertainty about what the technology is, what it does well, what it doesn't so well, and if it will make sense for you or your supply chain in terms of implementation. So hopefully today, I'm going to give you a nice overview of copper pillar, what the driving forces are, is it better than solder bump, and how it performs from a process and reliability perspective. So on the first slide, the obvious question is, where is copper pillar? And copper pillar really exists in flip chip, right? And so for us to really understand copper pillar, at least in terms of where it's going, where it's been implemented, whether or not I will see copper pillar in my product or on my board or in my package, we have to really understand and take a step back and talk about where is flip chip. And there is actually some fascinating information about flip chip, specifically in terms of flip chip versus wire bond. Now, flip chip has been around, oh my gosh, probably since, I think one of the first concepts of flip chip was only a few years after Jack Kirby invented the integrated circuit, believe it or not. And but there's kind of been a race between flip chip and wire bond ever since, one in which the death of wire bond has often been greatly exaggerated. And really kind of a great example is in the two graphs I've shown here. So the graph on the left, and hopefully you can see my, my cursor here, we can see that flip chip market has increased over the past 4 years, or is projected increase compared to the last 4 years. But wire bond is going along right with it. In fact, is growing even faster than flip chip. And the reason you can see why flip chip, even as it's supposedly a superior technology to wire bond, or at least a more advanced one, you can see why wire bond continues to kind of survive in this graph here on the right. And this is a great graph by Ms. Jan Vardaman, who kind of talks about the relative or the total package cost of wire bond versus flip chip and the effect of the introduction of copper wire bond. And what you can see is the transition from, in terms of a cost-effective package from wire bond to flip chip happens somewhere around 1,000 IO with gold wire bond. But when we switch over to copper wire bond, we can see that from a cost perspective, there are obviously other reasons to go flip chip and ipso facto copper pillar. Doesn't really happen until we got almost a 2,000 IO, really almost a 50 by 50 package. When it actually becomes cheaper to flip chip rather than do the standard wire bonding process. So wire bonding kind of continues to dominate, and looks like it will continue to dominate from a first level interconnect perspective. What's really interesting, I find, not just in terms of the fact that wire bond continues to extend its usefulness far beyond most prognosticators, but the fact that even as it dominates the first level interconnect market, there really is pretty much only one manufacturer of wire bond equipment. It's pretty much a complete monopoly for all practical purposes. But even as flip chip kind of has, has its place in the packaging world, but is not really taking over wire bond, the type of interconnect in flip chip is changing quite dramatically. And we can see that here in this graph by Yole. If we compare kind of copper pillar versus the other options, including gold stud, as well as a variety of solder alloys, we can see that as we pass into 2015 and beyond, copper pillar is really going to dominate, right? And we're going to kind of explain or understand why that is the case. So flip chip, you know, has its role in terms of certain designs and certain devices, but wire bond will pretty much dominate for a long time to come. But within that limited flip chip world, it's really going to be increasingly by, the interconnection is going to be increasingly be copper pillar. Now, just to kind of take a step back, and for those of you kind of who need a little introduction, what do we mean by flip chip and copper pillar? So what we're looking at here is a nice schematic done by my colleague, Dr. Gil Sharon, that kind of shows you all the aspects of a flip chip interconnect. And so there's our die in gray, the silicon. And here's our substrate, for example, part of the BGA, which is down here in brown, and the various interconnections in between. So we have our solder connecting our UBM, our underbump metallurgy, to our copper pad on the BGA. And we have a variety of other kind of layers that are on top of the silicon, including most critically the ELK active layer, which is extreme low K dielectric, as well as this purple layer here, which is our polyimide, which is typically used to kind of provide some degree of compliance or cushiness between the solder and that ELK active layer, because that active layer is quite brittle, quite fragile in terms of its mechanical properties. So this has been kind of the standard interconnect for many years for flip chip devices. And what we're transitioning to, we can see here, is we've replaced not the entire solder, so we call it copper pillar, but the final connection is still solder. But now we're replacing a good portion of that flip chip with a copper pillar of a variety of geometries and sizes, right? But our substrate is still the same, and our silicon, and most importantly, our silicon is still the same to some extent. The UBM might change to some degree, but these are kind of what we're talking about when we say flip chip solder bump and flip chip copper pillar. Now, to just give you a little history of the copper pillar, what's really quite impressive about copper pillar, and those of you who have been in presentations by me in the past, know the one thing I like to do is just kind of lay out the history of the packaging technology. And what's been really fascinating about packaging technology is how often it's introduced very early on, and how it takes a relatively long time for that packaging technology to go mainstream. Whether we're talking about copper pillar or copper wire bond or QFN, otherwise known as bottom terminated components, you know, it can typically take a good 10, 15 years before you'll really start to see that technology being used in the actual marketplace. TSVs, through silicon vias. Great example. They were talking about TSVs as early as the early 70s. If you look at the patent literature, and some initial attempts probably as, it still took 15 years before you saw any kind of publication on it, and really another 15 or 20 years before it actually got into some kind of mass production. Copper pillar actually doesn't take nearly as long, and part of it is because you're not really playing with the active portion of the silicon, right? That's a very touchy area people don't like to play with. So copper pillar is first patented by IBM in 2001. They call it the metal post solder chip connection. Typical IBM, they like their acronyms, right? And only 4 years later, after it's patented, we start to see copper pillar interconnects in one very specific area, and that's RF power amplifiers and front-end modules, right? And it provides a lot of benefit from an electrical stability perspective. It provides a lot of benefit from the thermal performance perspective, and it saves a lot of money, because the way the power amps and front-end modules were packaged required a lot of additional processes, including wafer thinning and backside metallization. All that goes away with the copper pillar, right? So there's a huge driving force to integrate that technology, right? So that's initially in a very kind of, well, it's hundreds of millions a year, but it's still kind of a niche area. But only about a year after that, Intel comes out with its combination of copper pillar and at that point tin lead joint for its microprocessors at 65 nanometer. right? And as we know, in some respects, what Intel does, as Intel goes, so goes the rest of the packaging industry, right? So it's a big, huge indicator when Intel releases its copper pillar technology, or what they call copper die bump, right, at 65 nanometer. So Intel in its marketing literature lists a number of benefits, including electromigration resistance. So copper pillar has a lower resistance than solder, and it's not heterogeneous like solder. So it definitely there's improvements in electromigration, and we'll talk about that in a lot more detail later in the presentation. We have better thermal conductivity. Copper is really one of the best thermal conductors out there, right below kind of silver and carbon-based forms. It simplifies the UBM, so again, fewer processes to build out, and most importantly, they can go to higher I/O density, right? So they can now they can have higher density on those bumps, and that becomes really critical as we go to these smaller feature sizes. So many believe that there is an additional side benefit to this copper pillar, is that it allows Intel to maintain a high TG underfill. So TG is glass transition temperature. It's the temperature in which the epoxy underfill goes from being relatively rigid and stiff to kind of rubbery, kind of very soft kind of material. There's a lot of companies, because of the weakness of the ELK or ULK layer that we talked about, they have problems with bump cracking, which again we'll talk about in a little more detail. I'm getting ahead of myself. But they have a problem with bump cracking, and to resolve that, they change the underfill material, right? We're not going to change what's happening on the silicon. Like I said, silicon kind of rules the roost here, right? Silicon does what it does, and we in the packaging world have to work around that. So they change the underfill. Intel does not, and the resulting change in underfill causes a lot of massive failures in a variety of technologies. The most well-known is GPU failures, but there are other technologies that use flip chip, high technology flip chip devices that at least we here at DFR have visibility into in terms of additional failures due to this change to low TG. So Intel kind of benefits either intentionally or unintentionally. But what's also very interesting about the benefits listed by Intel is that there's no mention about temperature cycling performance. And we're going to talk about that a little bit, but those are actually the introduction of a copper pillar may or may not improve thermal cycling performance, and in fact it may even degrade it depending on a variety of parameters. And that's actually one of the initial motivations for this talk, is really trying to understand what does copper pillar do in terms of thermal cycle reliability, because that's really, if we think about it, one of the biggest problems with flip chip, right? If I take a silicon which expands by 2 parts per million and I attach it to a epoxy substrate which expands by 14, and it's a relatively rigid attach, right? Typically, we think about these application environments where there's lots of power on and off, and we're seeing, as we go to lower process nodes, the die get hotter. It's going to be a real problem. So Intel mentions benefits, but if we think about the larger, broader industry, there's really one major driver for copper pillar, and that's smaller pitch. As you can kind of see here on the top right, as published by Reneus, and actually also down here in the middle as published by SBIL. As I go to finer bump pitch, which is important, well, we always like to go to smaller pitch, right? It allows us to shrink our die. But also we need to correlate our I/O structure with the process node, right? It doesn't really help if you go from a 90 nanometer process node to a 12 or 14 nanometer process node, and I have the same pitch. So once we kind of pass below 125 micron, and we can see that, Reneus has it around 150, right? And we can see SPIL has around let's say 110, but somewhere around 125 micron pitch, processing or manufacturing with solder bump becomes really problematic in terms of alignment, in terms of getting good reflow, putting down paste, avoiding bridging, all these things, right? And the additional benefits of going to smaller pitch, right, is also that I can reduce the number of substrate layers in the substrate, which also drives cost. And so in this day and age, I think what really drives packaging, because Apple makes 400 million smartphones a year, and Samsung probably makes 600 million, and everybody else makes another billion, right? It's all about size, it's all about performance, and it's all about cost. And copper pillar actually satisfies all three of those. Now, when I take this copper pillar, or when I take any kind of flip chip connection and I change it, there's a little bit of a balancing act going on. In fact, some people call it the 7. Right? There are 7 things that people tend to be concerned about when it comes to a flip chip interconnect that the copper pillar needs to be aware of. And we're going to try to talk about those 3 to some degree. Right? So it's a low K dielectric cracking, which I talked about, what some people call a white bump or bump cracking. It can occur during chip attach or during underfill cure. We're worried about flip chip reliability. Really, we're just talking about temperature cycling. Right, the dimensions are typically too small, or in terms of worry about any kind of mechanical like shock or vibe for all practical purposes, even though we continue to do the testing. Don't really know why. I'm also worried about solder joint reliability. So the flip chip interconnection can actually influence the reliability of the second level interconnect. Right, so not just so we can have situations we don't want to transfer the weak spot necessarily from flip chip bump to solder joint, especially if that transition makes a second level solder joint reliability much worse. We have concerns about warpage. Coplanarity is really critical for assembly. Worried about any kind of die backside stress, which can cause the die to crack. Bond line thickness, which is really critical for the thermal interface material, the TIM, right, and how well it connects to that heat sink or that lid. And finally, the electromigration benefit that Intel talked about, also increasingly a concern for flip chip. Right? Electromigration concerns are going off die and now into the interconnect itself. So, you know, DFR solutions were designed for reliability. One of the things we tend to be interested in or concerned about is reliability. So we are changing from one interconnect technology to another, and the question is there a risk? Should I be concerned? And as you might guess, the answer is depends. It really kind of depends to some extent, right? If it was always great across the board, I'd probably be out of a job. And if it was bad across the board, they probably, hopefully, would not implement it into the packaging technology. So it really kind of depends upon a variety of things. And one of the most critical things is to consider is there's multiple flavors of flip chip devices. So probably the most common, or the one most well known to us because we can see it in our computers, is the standard flip chip bare die with underfill, right? I have my substrate and my solder balls under my BGA that attach it to my PCB. And there's my die, and there's my interconnects, and there's my underfill with a little bit of a meniscus there. But I can also have a lidded device. So I take that same bare die, now I apply a lid, and then actually changes a lot of things more than you might realize in terms of the overall response of the package and where the stresses occur and how those stresses transfer from one portion of the package or the device to another. I can replace that lid with a molded device, but in this case the mold device has underfill and an exposed die, again for thermal interfacing purposes. I can maintain that underfill within this molded arrangement, or I can use I can pick a molding compound that works for molding as well as for underfill performance. Obviously, it reduces a higher throughput, lower cost, but introduces some degree of risk. And finally, it could do a complete overmold device, right? So again, I'm using the same material for both underfill and molding, but now because I don't necessarily need a complete thermal performance, I'm covering the entire die. And again, there's a change in terms of thermal stresses and mechanical response in terms of all these variations of flip chip devices. So there's different flip chip devices, which influence first and second level interconnect reliability. But there's also different copper pillars. So just take a second and take a look at all these different things that are called copper pillar, right? So we can see I've got skinny copper pillars and fat copper pillars, right? I've got long copper pillars and short copper pillars, right? I have copper pillars where the solder stays only on the bottom. I have copper pillar where the solder wicks up along the side, right? I have copper pillar where the copper pillar and the bond pad, and this actually is a trace, I'll talk about that in a minute, are similar dimensions. I have it where they're very different dimensions. I have a situation where the copper pillar is actually coming up from the BGA and not from the substrate itself, not from the silicon itself. So copper pillar comes in a variety of flavors. All of them play some critical role in terms of whether or not it'll be reliable. Just to give you a little more specific example, right, this is Intel above, as we talked about before, the first Intel copper pillar that came out about 9 years ago. We have an Amcor flavor here on the top right, okay, and we have here an ASC example here on the bottom right, right? So example here we can see, and again, this is actually trace, but what I'll describe it as, we can say this is solder mask defined on the BGA, this is non-solder mask defined, as we can see. We can see that we have some straight edges here, we have some tapering here. We can see that we really neck down the copper pillar at the point where it actually reaches the bond pad, not so much here with the Amcor design. And part of it is these design elements are partially, hopefully, designed to optimize what the customer needs in terms of performance and cost, and manufacturability and reliability. Part of it is actually avoiding patent issues, right? When there are 8 ways to do it and 7 ways have been patented, it can potentially drive you a particular configuration, even if that's not necessarily the best arrangement from a reliability perspective. So we can see from those 2 slides clear differences in terms of pillar dimensions and pillar shape. So we've seen square, we've seen oval, we've seen round here at DFR Solutions. You can taper it or you can have it grow straight out from the bond pad. And there are differences in terms of ratios of that pillar dimensions and other aspects of the packaging, such as solder thickness, UBM diameter, or bond pad diameter on the BGA. And then we can also have this compliance layer that we talked about before, this polyimide, which adds a little bit of a cushion. So I would love, in a kind of generic manner, to give you kind of a statement that copper pillar is better or worse than solder bump in a particular situation, or maybe in general or in a particular situation. But again, all these variations kind of complicate that effort. So we have differences in geometry in manufacturing. We also have differences in regards to the manufacturing process itself. So there are a couple ways of doing copper pillar. You can do the standard reflow process with solder paste that you've been doing with your flip chip device, the solder flip chip device. And that's what a lot of manufacturers will do at the coarser pitches, maybe where they've gone to copper pillar for reasons other than a finer pitch. If the pitch gets too fine or the bond pad on the BGA gets too small, it becomes very difficult to do an effective stencil print, right? So then you can just go to a simple flux dip instead, right? Allows you to avoid some of those challenges, but maybe not necessarily as effective as a soldering process. Also possibly maybe a little more of a risk in terms of the underfill to the BGA, as well as risk in terms of a moisture sensitivity level, right? Increased MSL risk there if I don't have good adhesion. What we're increasingly seeing in terms of the dominant assembly process is thermocompression bonding. So I'm actually not doing a classic reflow. I'm actually heating the device and applying pressure. What's amazing about that is, and I'm using non-conductive paste to do it. Okay. And I'm just kind of using a cap on the top of the solder, using a cap on top of the solder pillar as my assembly material. So typically once we talked about just to recall, we said really once we get down to about 125 micron pitch, it really has to be copper pillar. And if I get below 60 micron pitch, it's going to be copper pillar with thermocompression bonding and that non-conductive paste. There's some benefits to it. I mean, the process only takes 2 to 3 seconds, right? So as fast as wire bonding. Now, of course, I can't put it all in a single reflow oven, so there's, again, some trade-offs there. One of the difficulties is now this non-conductive paste becomes my underfill, right? I'm no longer underfilling in this situation, or at least I'm not having the classic underfill process, which is post-assembly, at least post-assembly of the die to the substrate. My NCP is my underfill, right? So it helps me with my process, and it becomes my default underfill. So now I've changed the material, and there are other material requirements for NCP beyond the standard underfill because it becomes part of the assembly process. And the result is we find that the NCP typically has a lower glass transition temperature and a lower modulus than standard underfill. So we're finding an increasing move more towards low TG underfills, which again can be problematic, which I'll talk about in a minute. And underfill is important because for the most part, at least based upon our experience with flip chip devices, solder bump flip chip devices, underfill is going to dominate any kind of thermal cycling performance. So let's talk about those 7 drivers and talk about some of them right now. One of them is electromigration, again, kind of one of the highlights from Intel's perspective. And when we're talking about similar dimensions, copper pillar is definitely much better, okay? Outperforms solder bump by as much as 3x, right? And there's a number of reasons for that. Higher electrical conductivity is one, higher thermal conductivity is another. You can see on the bottom right graph, we can see that the current density, which is directly related to performance of the, in terms of electromigration, we can see that under the same conditions, same test stresses, the current density is going to drop by roughly about, let's say about 40%, right, compared to the solder bump, right? And as I talked about before also, we've got some much more uniform microstructure with the copper than I do with either the tin lead or the high lead or the SAC 305, right? Now, having said that, one thing to be aware of is where are we most worried about current density? It's not necessarily in the bulk bump structure or the flip chip or the copper pillar. It's actually at the entrance, right, is where we come in. And this is where it becomes really interesting. I'm probably getting ahead of myself, right? We have this trade-off, right? In order to avoid ELK cracking, right, we are changing these diameters of the copper pillar to the bump properties, and that can affect my current crowding in that exact location. And I'll reiterate that in a couple slides, but something very important to think about. Now, in addition to some of the tests done by some of the simulations done by SPIL, Amcor did a great series of electromigration tests authored by Syed, who is now at Qualcomm. And you can kind of clearly see this table here. It's really kind of ranking from best to worst, right? From copper pillar to lead-free to eutectic tin lead to high lead, okay? You can clearly see if we just take one example right here, let's take the worst case scenario of 700 milliamp stress current and 150 degree C oven temperatures, right? We see the copper pillar has no failures out to 6,300 hours, whereas the lead-free pretty much had full failure after 4,000. The eutectic had full failure after only about 1,200, and the high lead couldn't even make it out to 1,000 before it had failures, right? So if your design or the design that you're using is at risk of electromigration, copper pillar seems to be the clear winner when we have similar dimensions. But that's a big caveat, right? So we're not going to have similar dimensions. Solder bumps are typically 80 to 100 micron diameter. The copper pillar is going to be much smaller. We like it to be much smaller because we're going to finer pitch. right? And as we talked about, one of the most critical things, and let me find an example for you again, I'll just reiterate that. So here's a good example, right? So you can see here, right, this image at the bottom right, ASC, I've necked down this copper pillar. Now, why do I do that? Well, it gives me a lot more compliance on the structure, and I don't introduce as much stresses into that ELK layer, which is just above it, right? Which is great, right? So I avoid my ELK cracking, but now look at this, right? I'm talking about my diameter here is far smaller than the solder bump that replaced it, or that's been replaced, right? So if I really, you would think sometimes an apples to apples comparison, you would have the dimensions the same. But in reality, if you really want to understand electromigration risks, the apples to apples is what was there before and what is replacing it. So from the AMCOR perspective, you can see I've got a big solid chunk of copper here. Yeah, the diameters are almost equivalent. But here with the ASC approach, the diameter is much smaller. Let me move on to where we were before. There's our SIAD results, right? So we got a ratio of that interconnect, right? So that bump or pillar diameter to the UBM, right? So that's going to decrease to reduce that stress and locate dielectric, but that's going to cause an increase in current density. And then increasingly, we have a huge interest on what's called bump on trace, right? So because I've got this copper pillar and I've got some pretty good controls on the copper pillar, the thought process is I no longer need a specific bond pad on my BGA. I'll just find a part of the trace that I want to connect to. I'll solder mask kind of around it, and boom, I just solder directly to the trace. In some respect, it's really quite clever and frees up quite a bit of real estate, right, that was typically been taken up by bond pads. And also adds, again, some additional compliance, which may help with ELK concerns or risks, especially during the cure of the NCP. But again, I'm going to have a much smaller diameter in that area, and so I'm going to have a much higher current density from that perspective. So that is kind of some things to think about in terms of electromigration. In general, better, right? But we're moving in a direction that's going to make electromigration reliability challenging. From a thermal cycling reliability perspective, in general, the performance is expected to be better. Expected. So I tend to get actually higher standoff with copper pillar than I get with solder bump. So I get a little more compliance in the interconnect structure, even though copper is a stiffer material than tin-based solders. I also have less solder from a volume perspective, but the surface areas are roughly the same. And so theoretically, I get a little more intermetallic forming in that solder structure, which theoretically should actually improve my creep resistance, which is why SAC 405 is better than SAC 305, which is better than SAC 105 when it comes to thermal cycle fatigue. And there are studies that kind of have proven this. You can see here, right, this is one kind of extreme example here on the bottom left, right? A lot of intermetallic has formed. This is based upon an aging study. But even here, with Jan Vardaman's cross-section, and actually here, this is a great example of to the extreme lengths people will go, right, to reduce that stress on that ELK layer, right? Very, very small diameter. Now, again, if this application has relatively low currents, right, why not? And then you can even see here this one application looking at changes in intermetallic as a function of temperature cycling. You can see definitely a much larger increase in intermetallic layer and a much smaller amount of tin as we go from 0 cycles to 1500. Which actually then begs the question, how difficult will it be to predict temperature cycle behavior if we're seeing such a dramatic change in the morphology of the solder itself. But as much as the intermetallic is potentially good, there is really kind of as a yet unknown balance between a high percentage of intermetallic, which theoretically is good, question mark, and a small solder joint height. Because if the production process isn't optimized, what can happen is this solder can actually wick up the size of the copper pillar, right? So as the solder wicks up the size of the copper pillar, it's going to pull this copper pillar down, and we're going to have a smaller solder joint height. And as we've seen with QFNs, and I'm sure with copper pillar, we're going to really decrease the time to failure if I don't have some degree of solder joint height on that copper pillar. And that's actually been one thing that's been very interesting. If you look at all the copper pillars that we've talked about, right, they all maintain, except for maybe this one from TI, they all try to maintain a relatively good portion of solder joint height. So the copper pillar is not replacing the solder completely, right? And part of that is because of, I think, solder joints' sensitivity to failure and temperature cycling when there's a relatively thin joint. So all these kind of uncertainties regarding copper pillar really plays out if you actually look in the literature in terms of what it says about copper pillar. So the first thing that's really interesting, and that's actually my point on the next slide, is surprisingly little data on copper pillar temperature cycling performance. Either you get 0 failures after 1,000 cycles, which is the standard marketing fluff we all see sometimes, or you get a lot of simulation, but not a lot of test data, right? So if we rely on the simulation, right, we see contradictory predictions. So some claim lower stress. This is M. Hishai in 2012, right? You can see they're looking at comparison of stresses here, right? And they're saying, look, the stresses with lead-free solder, the bump stress, right, with lead-free solder is a 1, right? So this is all normalized. So the bumps are a 1. If I go to copper, I'm going to increase the ELK stress, but there's ways around that like we talked about. I'll increase the UBM stress slightly. The warpage is about, you know, pretty much the same. But look, I greatly reduce the stress in the remaining solder, the bump stress, right? So they're claiming that we're going to have a better reliability with copper pillar. But Hua Yang, right, when they look at inelastic strain energy, right, they're finding that I go to a pillar, my inelastic strain energy is increasing by roughly, let's say, about 20 to 30%, which is definitely going to result in a worse temperature cycle performance, right? Now, regardless, and one of the challenges here is we can't really be looking at copper pillar versus solder bump because the underfill properties are going to dominate, right? And as we talked about, the underfills are probably going to change, especially as we go to these lower pitch designs, right? We're going to go to that NCP material or NCF material, and that's going to have a far greater effect on interconnect parameters potentially than just solder bump versus copper pillar. And one of the things we've been talking about actually just very recently here at DFR is to really think, right, I mean, it's really to take that physics of failure concept and apply it to every aspect of electronics. Ask the questions, right? If you ask the right questions, you get the right answers. And so the questions we're asking here that we don't always unfortunately see in the supply chain is, what happens in terms of underfill when I change the interconnect structure, right? And I think, at least here at DFR, there's some uncertainty as how well that mitigation from the underfill will be present and whether you can accurately capture the mitigation effect during simulation. So let's think about underfill for a second, right? What does it do? Well, it shares a load, right? If I stuff more material between the flip chip, the die, and the BGA substrate, right? They're all going to share the load, so there's not much load on any one individual solder joint or flip chip joint, right? But if you run the calculations and you compare it to actual performance, it's not just the load sharing. It doesn't correlate. The load sharing would maybe double the lifetime, maybe triple, but you can see 10, 20, 30x improvement in terms of reliability by using underfill. So it's not the load sharing, it's the fact that the underfill is placing the solder under compression, right, during the cure process pulling the die down, shrinking around the balls, and it's the compression which is believed to be really a major driver for underfill performance, right? And we'll talk a little bit about an aspect of that which we call kind of mean stress, right? But we believe here at DFR that the copper pillars are probably not going to be as sensitive to that benefit, right? I have less solder exposed to underfill. It can't, it's not compressing the entire flip chip bump. It's only compressing a small kind of sliver of solder between the bond pad and the copper pillar, right? And the copper pillar is a little more, has a higher modulus, so it's going to be a little more resistant to it, right? So it'll be interesting, but I would not be surprised if underfill is not found to be as effective with this new structure as it is with the flip chip solder bump. In fact, it's almost like serendipitous, right? We're able to use underfill. Underfill really brought about the revolution of flip chip. Before that, you had to put flip chip on ceramic, which was really expensive and kind of a pain, right? So now I can put flip chip on organic substrate because I've got this underfill. But the underfill benefit may really be derived based off the material and the geometries that we were using. So as we move to NCP, right, and we move to the interconnect structure, underfill may not be as effective. And as we change to the underfill, we have other problems as well. NCP is going to be a lower TG, as like I talked about. And when I decrease the TG, we have to be really careful that that TG is not within the operating expectations of the device. So a key thing to be aware of is if I test -55 to 125, and I have a low TG material, like 75 to 80 degrees C, it will always pass with flying colors. In fact, it's almost indestructible. So if you find out your device manufacturer is using a low TG underfill, and they tell you it passed -55, 125, you can take that data and you can throw it out the window because it is irrelevant, completely irrelevant, okay? And part of it is why you can see right here. The CTE is going to change before the modulus. So what ends up happening is if you have an application that is kind of more in this area, kind of below the TG, you're going to experience a lot of really high stresses. But if you have a test condition which goes far beyond, okay, those stresses are going to reverse. And when they reverse, you end up having more of a compressive stress and a relatively, a much longer time to failure. In fact, you can do a compatibility displacement and clearly see as I approach that T sub G, I'm getting really, really high stresses, right? I mean, it goes up by, 3, 4x compared to if I'm on either side of that T sub G, right? So if I'm on this side of the T sub G, really low stresses, nothing to worry about. On this side of the T sub G, way down here, nothing to worry about. But if I operate in this regime, really rapid times to failure. And unfortunately, the industry doesn't seem or doesn't want to seem to have learned from this kind of experience. And so what's really bad is not just the fact that the stress is higher, but the direction of the stress as well. So when I get this stress that is tensile, right, I can have times to failure. So it's not just the stress, but also the damage. The damage accumulation is literally almost 2 orders of magnitude faster when I have anything in tension than I have it in shear. And we at DFR have seen that, unfortunately, in multiple cases, not just with flip chip devices, but also with potted materials, materials that are overly constrained, boards that are overly constrained, even boards that go through thermal shock. If there's any kind of like bending, warpage, tension occurring, very, very fast times to failure. So also, as we talked about, the consistency of the solder becomes very critical. We don't want any wetting along the sides. It can result in a very, very small bond line, right? We can also kind of get some insufficient also if we have any kind of insufficient coplanarity of the copper pillars, and depending upon the manufacturer, you can have variations as much as 25%, so 40 to 50 microns, right? That may not be much for the copper pillar, but that can be a lot for the solder joint underneath it, right? So some solder joints can work out really, get a really nice kind of joint, and others can be much thinner based upon that variability. kind of the last aspect of thermal cycling reliability that can be somewhat confusing is you can actually get a shift in the failure site as well. So typically when we do thermal cycling, we're really focused on that solder joint between the copper pillar and the bond pad. But depending upon the temperature cycle condition, we can also drive cracking in that low K dielectric as well, right? So again, without really understanding when that failure site shifts, right, we can run a test that induces one failure, and we can be in the field and have another failure occur. And so again, in the case of the qualification test, is no longer representative of what my concerns are when I actually use the product. So speaking of ELK cracking, right? Well, I would say that a third of the 7 that we are concerned about, right? And in fact, ELK cracking is often viewed as the biggest risk in regards to transition to copper pillar, right? Primarily occurs when the flip chip is bonded to the BGA, but also can occur during underfill cure. But there, they have a little better kind of, I think, feel in terms of how to mitigate. And we've already talked or touched upon it several times during the presentation. So if I have a nice tall copper pillar, it's going to decouple that interaction between the copper pillar and that ELK dielectric, okay? But as with everything, right, that's why engineers are so important, right? There's always this trade-off, right? Really tall copper pillars work really well, but it takes a longer time to build them up because it's all a plating process, right? You can also increase the ELK thickness, but that means I'm doing something on the silicon side, which can be problematic. I can make for a larger diameter copper pillar, or as we again talked about a lot, we can reduce that attach, right? That very small attach at the top or at the silicon point of connection, or at the bottom, like that copper pillar on trace that we talked about as well. And then the polyimide, which is that cushion, also helps with the ELK. Just to give you a little sense of actual quantitative benefits. So this is again a study by Y Yang looking at ELK crack mitigation, comparing kind of 80 micron versus 100 micron diameter copper pillars. You wouldn't typically think that's a big difference, but you can see here we look at the energy release rate. There's actually quite a significant difference between large and small pillar diameters. And what's really interesting is he actually tracked it based upon where in the buildup, right, that crack could possibly occur and evaluating that risk, right? So you can see here what he finds at crack 3, which I'll just kind of show you with my cursor, is right down here, right below metal 3 layer, is where he finds the highest energy release rate. And for those of you familiar with fracture mechanics, most brittle materials have a critical energy release rate above which then you'll end up cracking of the interface or the bulk material itself. Right, so the higher the energy release rate he's measuring, the more likely that crack is going to occur. And you can see rather dramatic decreases in terms of the energy release rate if they move to a larger pillar diameter, even when only 20 micron difference. Right, and then the small attach again we kind of talked about. You can have that small attach on top, right, or you can have that small attach on the bottom. Top being the silicon and bottom being the BGA, right. Now, SPIL recommends to its customers that bond pad ratio to trace width ratio not exceed 2x, right? So this U to L shouldn't be more than 2x, or it runs into manufacturability processing issues. And then kind of finally, another mitigation for the avoiding ELK is that polyimide passivation. It's relatively soft. It's not like soft like silicone, but it's softer than the other materials that are around it, so it can reduce that stress, right? So the bump pad interface diameter is reduced, right? The copper pillar height remains about the same, right? But we're gonna bring in that pad diameter, as you can see by comparing the image on the left to the image on the right, and we're also going to bring it up a little bit as well, right? In order to get that polyimide passivation right in there. Right, and there is actually what's really nice. There is some flexibility in terms of the PI layer. It can actually be done at the foundry, or it can also be done at the OSAT. Are 2 options. So in conclusion, copper pillar is increasing in popularity, right? The challenge is each OSAT and potentially foundry has different technologies and processes, and these variations, can be challenging in terms of improving, predicting, mitigating reliability and risk, right? The key thing to be aware of is don't always rely on test. Please do not always rely on test, right? If you have a new technology coming in your supply chain, the first thing to do is simply ask, critical, thoughtful, physics of failure-based questions about the technology. Maybe your supplier has done the due diligence that demonstrates a robust product or process. Maybe they haven't, but you'll never know if you only base it on the test.
Craig, please elaborate on test conditions that give better correlation to field use.
So it's a little challenging. What we recommend that people do is ask questions about the stress conditions under test and the stress conditions in the field. What we don't want to do is completely change the stress conditions. So let me elaborate a little bit more. When we were typically only worried about shear, right, and that's typically the failure mode for most solder joints and electronics, right, the shear is non-directional for all practical purposes, right? So doesn't matter, what the stress state is, shear is shear, right? It's non-directional. But when we move into discussions about compression and tension, which can be the case with changes in underfill as well as changes with the copper pillar, we have to ask questions about compression and tension, right? And is there a risk that somehow I'm switching from one state to the other if I compare test to field? If I'm always in tension under test and I'm always in tension in the field, or I'm always in compression under test and always in compression in the field, for the most part the two are going to correlate really well, right? And you're going to be fine. It's when there's a flip in one and not in the other is when we see large deviation and variation in terms of performance.
Okay, I've got one more here. What is the most common cause of reliability failures in copper pillars?
So the most common failures that we've seen, I would say, divide evenly between temperature cycle issues and ELK cracking. We ourselves have not seen a lot of electromigration failures in copper pillar. The ELK cracking we find is typically the manufacturer doesn't really clearly understand the variability. I guess I would say they don't understand how close they are in terms of cracking the ELK. Right, it's that margining. So we find when manufacturers just kind of run a qual and determine that the ELK is not cracked, then they start producing. They fail to realize what changes in parameters, either in terms of geometry or process, may kind of tip them over the edge. And with a brittle phenomenon, that's a real big risk, right? Because with brittle fracture, it's going to be either on or off. There's not going to be any kind of indications of a problem. With temperature cycling, the biggest issue we find is wicking up the copper pillar. So if the process is not well controlled, or they don't use the right plating arrangements, they'll get a lot of solder wicking up the copper pillar, and they get really thin bond lines, and they get times of failure that are really, really short, far shorter than they would expect.
Okay, I've got another question here. How does polyimide affect the stresses in the ULK or ELK?
So it reduces the stresses in the ULK or ELK. If you can imagine, what's occurring is there's a degree of rotation that is occurring with the copper pillar, and that is cracking the ELK. It's kind of putting, if you imagine it's rotating, it's kind of pull, on one side it's going to pull on the ELK or that interface and break it. With the polyimides, we're doing two things. We're shrinking that connection, so it's a little more of a pivot point, right, as opposed to a hard connection. And when it kind of starts to rotate, right, the polyimide kind of compresses or expands and takes up a lot of that kind of rotation, at least initially. It's not a lot of rotation needed in order to cause that cracking to occur,
Okay, and I think we have time for one more question, Craig. Have you seen or have you investigated the reliability of copper pillars during high temp storage? And have your simulations predicted solder moving up the pillar or along the trace?
So that's a very interesting question. I've not, I guess I'm trying to think of the mechanism that would cause the solder to migrate under a high temp condition. Typically, the solder moving up the pillar along the trace is during the soldering process, not during a high temp storage environment. In terms of reliability of copper pillars during high temperature storage, the primary concern is the formation of intermetallics. We have not had an opportunity to kind of dive into that into a lot of detail. So unfortunately, I don't have any kind of good quantitative data in regards to that environment.
Okay. Once again, thank you, Craig, and thanks everybody for attending.